office hours today?
Yeah, after class. Okay, I do have the first exam graded, and the scores were far lower than anticipated. I will have to figure out something to do on that front. I wanted to go over some of the problems people had. So looking at this first one, most people realized it was a force problem, but even those people didn't put the force arrows on their picture and have, some of the forces is zero because it's an equilibrium. Right, so that was just some of the forces is zero because it's an equilibrium. You have the spring pushing out, the force of the electrostatic force pulling in because it shrunk. And then there were obscure mistakes. I'll name one, Chad.
I am an obscurist.
He had written delta x equals 0.21, and delta x squared is equal to 0.54 squared. Right. So those I know you knew what you were doing. It makes sense now, he says. Okay. The one with the 3 spheres, you have a net force of 0 on either sphere on the edge, which means either sphere on the edge has to have a force pushing each direction. So once again, your picture should have had the force arrows. And then you say for the forces to be in opposite directions, then the 2 other charges have to be opposite signs. And you end up with the situation then that QX and Q2 have to be opposite signs, but QX and Q1 also have to be opposite signs, which means the Q1 and Q2 have to be the same sign. This was the first of the 3 pictures where I said I needed you to add something to it, and only about 3 people added anything to it. What you needed to add was the electric field vectors, because you need to just add those 2 vectors. And so the problem itself was most people, well, a lot of people, calculate the magnitude of the 2 electric fields. You have to add them as vectors. There are some people who tried to add them as scalars. But there were a lot of people who lost the point of the picture because they just drew the original picture and didn't put in the electric fields, which was the additional part that I needed. This one here, that was, we've said it so many times, it's probably just like flies right by you at this point. But charge, everything always goes to lower potential energy, because lower potential energy means you're going the direction the force is pointing. But because it has a negative charge, and you have that relationship that the change in potential energy is Q times the change in voltage, change in potential, then for change in potential energy to go down, the change in voltage has to be up. This one here had great confusion. I don't think there was a single person who plotted the electric potential from each of the 2 charges and then tried to add them up. Right, but that's what you do. Electric potential is a scalar, whereas electric field is a vector. That's why electric potential is easier to work with, because you can just add them up. So the positive charge has a positive electric potential. The negative charge has a negative electric potential. And since the negative charge is not as big, remember the equation for electric potential is V is KQ over R. The smaller negative charge is going to drop off more rapidly. Notice they both go to infinity at the charge. That's why I don't have a peak where they come together, because they go to infinity. But the negative one falls off more rapidly so that you get back to positive if you go far away. And if you have a hard time with the idea, I get back to positive if I'm far away, just say, okay, if you're really far away, it just looks like one charge is the 2 combined. But plus 12 plus minus 5 is plus 7. So if you're really far away, it just looks like a plus 7 charge, so it has to be positive voltage when you get very far away. And then we get to the second one where I said you just need to make a minor adjustment. A lot of people took away the capacitor completely for their second circuit. The difference is you have a capacitor with a different kappa. In the first case, it was empty, which means it's air and has kappa of 1. In the second case, it had kappa of 3.1. So that was the difference in the two figures. You're changing the kappa, the dielectric constant, and thus the capacitance. And since capacitance is kappa epsilon 0 area over separation, there are some people who did a very fine job, actually went so far as to calculate the area over the separation and then put it back together to find the capacitance. Other people just stuck with, well, since capacitance is kappa epsilon 0 A over D, then capacitance 2 over capacitance 1 is kappa 2 over kappa 1, and got that quicker. Virtually everyone had this equation at least. That was not a problem. Okay, then we get to, I skipped one, didn't I? Here we go. I put this one on because I figured this one should have interest to a lot of people. My picture there is a little different than what I drew on everybody else's, because on everybody else's I put the power supply over here. If you look at your graded test, you'll see it has the power supply here. Yeah, of course. They will be scanned and returned today. You have the capacitor that you charge up to 4,200 volts. And so you're storing energy, because that's what capacitors do. They store energy in either a charge separation or electric field, depending on which way you want to talk about it. And then you're going to dump that energy through the body in 3 seconds. And the question was about the power. And so power is the rate at which energy is converted. And so we know that for a capacitor, the potential energy is 1/2 CV squared. We worked that out in class. We showed the graph showing that the voltage changes as you move the charge across. And so while it is very true that the change in potential energy, or work required, to move a charge through a voltage difference V is QV, the V value is changing as you charge or discharge the capacitor. So the total is not going to be just use Q, the total Q that you store on the capacitor, times V, the total V. And in fact, we worked out in class that the potential energy was 1/2 CV squared. And so the change in potential energy starts at 1/2 CV squared, ends at 0. So the amount that delivers to the body is the 1/2 CV initial squared. Divide that by 3 milliseconds, and you get the average power. There were some people, and some people, 3 or 4 people, who used VRMS and IRMS. The problem with that is they used the values for VRMS and IRMS for a sinusoid. Right? For a sinusoid, VRMS is equal to V peak over square root of 2. Now, we haven't studied this in class, but it was on the equation sheet. But these aren't sinusoidal voltages. And if you calculate the RMS voltage, it goes to 0. And so those equations aren't the appropriate equations. Because you had 1 over square root 2 twice, people end up getting the right answer with that, but it was a right answer due to random coincidence rather than any correct calculations there. So, well, things that I find interesting is they're delivering about 74 kilowatts of energy in 3 milliseconds. The energy stored, I did the energy calculation separately because I thought that was an interesting number. The energy stored on the capacitor is 220 joules when you have it charged to 4,200 volts. You might remember in class I said depends on your defibrillator if they talk about the voltage you charged it to or the energy that you're going to deliver. But the two are related to each other through that capacitor. Okay, then we get to the circuit problem that was a series versus a parallel circuit. And virtually everybody got the three equations right. You have adding resistors in series and parallel and Ohm's law. There were different methods from there. Some used very intriguing methods. And I don't know, that one had a fair amount of people that got it right. And the circuit problem, well, thankfully a lot of people got this right. It was on the practice questions. You just had to apply Kirchhoff's voltage law and Kirchhoff's current law, so you had to have the two equations, and Ohm's law, and then you make your three equations, two for the meshes because you have two meshes, one for the node because you have two essential nodes, you can only use one. And then you solve them in whatever method you find necessary. The final one was the Gauss's law problem. And there were only maybe two people who even mentioned or wrote the equation for Gauss's law and the Gauss's law problem, which is a bit of a problem because you really can't solve this without Gauss's law. Now you can find the charge at the center by using either Gauss's law or Coulomb's law, because you know the electric field 8 centimeters away, and from Coulomb's law, electric field is kq over r squared, and because the electric field lines are pointing in, whoops, I have one of them pointing out. Because they're pointing in, you know that's a negative charge in the center. So that part you didn't need Gauss's law for, you could use it with Coulomb's law. But then, the part that you had to add to the picture was, and of course, no one added this because nobody used Gauss's law in the Gauss's law problem. If you're going to find the charge on the inner portion of that conducting sphere, you need to have your Gaussian surface so that it is enclosing the inner portion of the conducting sphere and everything inside, but not enclosing the outer portion. And if you set up that Gaussian surface, and one person did state this very clearly, picture, right? That the electric field in the conductor is 0. And since the electric field in the conductor is 0, that means that the flux through that shell is going to be 0. The Gaussian surface is going to be 0. And if the flux is 0, how much charge has to be enclosed? 0. So that tells you the charge on the inner surface plus the charge of the center has to add up to 0. And that's how you get the charge on the inner surface. And that's really the only way to calculate it. And that's the end of the test, except for the calculus people. Calculus people had one more. They did, instead of that one, they did a different Gauss's law problem where they had to integrate to find the charge enclosed. What did you get here, Twisson? What did you get here? What was his answer? In time. Were you here at the beginning of class? Were you here at the beginning of class? You were?
I was like 1 minute late.
Okay. I had you and Jaron is not here at the beginning of class. Now I see you're here suddenly. I'm like, wait. Okay. So they had to calculate the charge enclosed, and then they had to use Gauss's law using that charge enclosed. Okay, any questions about the test? I mean, you know that this solution is on Moodle, right? You can go through and you can look at it. So when your test will be returned on Moodle this afternoon, and you can go look at your test and look at the solution, and you can always come with questions if you think I graded wrong or unfairly.
What is new solutions installed? Because I thought there was last year's solutions posted. Or like what category is it or something?
It's right under the exam.
Okay. It was last year, but maybe I'm blind.
When did you check?
It was like last week. You said they were.
Okay. Well, okay, there are two places where the exam solution is. It was actually on the place where I have the lecture slides by class time on Wednesday, but because I had two students who had not taken the test yet, I didn't advertise that. After they took the test, then I put it up on the main page of Moodle as well. Yes?
What was the highest grade and the average grades?
I don't know yet.
Is that something that will be told?
Well, you can always check on Moodle.
It says where the average grade is?
When you look at, it says on your grade thing, I think what the average grade on each assignment was. And if you look at the grade breakdown, you can look at each assignment and see what the average is and how many people got in this range and got the whole 9 yards.
Is there any potential of this test being correct?
I will do something with it, yes. Not just potential on this one. Divided by 2, that does not sound very fair. You got 72, but 36, that'll cover it. Yeah. I don't even know what the high score average is yet, so I can't say what I'm going to do. Tusam. The one we had to find what? The resistance, yeah. Should be right here. So once you find that the series resistance is 25 ohms and the parallel resistance is 5 ohms, you take the equations for the series resistance, R1 plus R2, and the equation for the parallel resistance, 1 over R is equal to 1 over R1 plus 1 over R2, and you have to just combine them algebraically, and you get a quadratic, and you solve that quadratic to get your 2 values. And the lower one is what it asked for. Diksha.
Just a general question. On the Moodle page, you have other exam solutions. Is that just from exams?
There's also other exam solutions there as well. Yeah.
Okay, that was for
But there should be one. I think I named it Exam 1 2016 Solution or something to that effect. We are looking for people to tutor, but like with last semester, so far everyone I've asked has said no. You can always come for help from me. Okay, going to today's lecture material, we'll start with a clicker question. How can an electric motor continue to operate with a No, Jared, you have to read the question first. Yes, I did not realize that it had gone away. How can an electric motor continue to operate with a DC battery powering it? Okay, the numbers are getting better. Stop it there. 0, 6, 6, 5. It's slowly moving in the right direction. By the way, this does remind me of Concept Coach. For today's Concept Coach, I'm considering just finishing Chapter 22. And then Chapter 23, I know I had said Chapter 23 before, but I looked at what I'm talking about today, and it's still 22. So for class on Wednesday, it probably says we're starting Chapter 24, doesn't it? Does it say finishing Chapter 23? Well, we will be starting Chapter 23, so let's say the first section from Chapter 23. Make sure you have that done by class on Wednesday. Because, I keep looking at things, I've got to cover this. Oh, this is great stuff. It slows me down. Okay, so now, on this, the reason I was shaking my hand, saying in my head, these people hate me, is because while that exists in Back to the Future, it doesn't exist in real life. Yeah, it sounds good. That's why they use it in Back to the Future. I mean, we've been talking about Gauss's law, and you use the flux, right? And we're going to talk about using flux for magnetic flux as well. So it sounds really good, but it's not. So that was not the answer, since flux capacitors don't exist. So that leaves us with only two viable options: the use of a split armature, or there's no way to make a DC motor work. Well, I'm here to tell you, DC motors work. Pretty sure this one up here says something about a DC motor, doesn't it? Oh, no, that's a generator. I thought it was a motor. Okay, it's a generator. Well, a motor and a generator are the same design, hence the confusion. But yes, there are DC motors. But a DC motor, you have to do something so that it doesn't, remember I talked about have maximum torque, you rotate 90 degrees and you have zero torque. If you rotate further, you can start having torque in the opposite direction. But if you can change the direction of the current, then you would flip the direction of the torque. And so what you have is what we call a split commutator. I said split armature here. Nice work, Richard. Yep, that's what confused you. You have that split commutator, which actually you didn't see this because I went past it. But in the first picture, here's a picture of a split commutator. You have the brushes. See the pretty brushes here. And then you have the split commutator there. So as it rotates, the side of the wire that's making contact with the positive is always the one that's on the left side. And so it's always going to have a positive torque. Now, 2 slides later, I have a different version of that question. Do you have, or a picture? Do you have a question?
No.
No. Okay. So here's a picture of a realistic electric motor. Now, if you look at this electric motor, what's different between this electric motor and the electric motor we discussed in class on Wednesday? There are a number of significant differences.
It's not like the wire thing that's rotating.
Okay, it's not just a loop that's rotating. That's the biggest thing right there. So let's focus on that. Now we see the split commutator over here on the left. That's, I think, rather easy to see in case you're not seeing it. There's little metal pads on the rod. The blue and white are just artificial to remind you there's 2 sides. But the blue and white are where you have the electrical contact with those brushes. So you can see it comes around and it will flip which brush is touching which pad. But over here, instead of just a loop, it's a bunch of coils around something metal. Now we're going to learn a lot in the coming days about what that metal is for. What do you suppose the multiple loops is for? What was the equation for torque? Let me write down the equation for torque to help us out. Get to that one. The torque equaled I NBA sine of theta. So why would we have all of those loops? To increase the torque. Because what relates to torque that has to do with loops? Well, everything does, but with multiple loops. Which one of those variables has to do with multiple loops? N. Because N is the number of loops you have. So having more loops is increasing your torque. Now having this material inside, that's actually going to change something that we don't see in our equation. It changes what we call the magnetic permeability of the coil, and it increases the magnetic field by as much as 1,000 times, which increases the torque by as much as 1,000 times. So that makes it a much stronger motor. Of course, it also adds mass to it, so that means that you're, for the same torque, you're not going to have as big an angular acceleration because you added that mass. But for 1,000 times more torque, you might have, 1,000 divided by 10, 100 times, the angular acceleration. You're generally willing to go with that. So this is just looking at design of the electric motor. And like I said, we will learn in the next chapter. Hey, look, I did it a second time because I copied it and forgot to delete the original. Go forward. We will learn with the electric generator how this works in reverse. This here looks like an electric motor, but at the top of the slide it doesn't say electric motor, it says galvanometer. The galvanometer is something that will measure how much current is going through a wire. And the simple design for a galvanometer is that you have a loop in two magnets that looks just like the DC motor, right? But then you have a spring. And so you apply torque, and the torque makes it start to rotate, but the spring produces a counter torque. And so you reach equilibrium where the torque from the spring, and for a spring you can actually calculate the torque here as torque for a spring is equal to, believe it or not, we'll use the Greek letter kappa. Kappa theta for the spring. So the torque is proportional to the angle that it rotates. And of course the torque for the coil is equal to I times NBA times sine theta. Now you notice one has sine theta and one has theta. For small angles, sine theta is approximately theta. So if it only moves by 5 degrees or so, it's pretty much the angle that it moves tells you what the current is. If it moves by like 15 or 20 degrees, then you lose that linearity. It takes, you're going to have a varied scale. So to have a uniform scale like it shows here, it has to rotate only about 5 degrees or so. But that's cool to know, isn't it? Yeah, thank you. Thank you for humoring my fantasies. All right, Ampere's law. In all truth, I did not check to see if the textbook has Ampere's law. I'm guessing it doesn't simply because it didn't have Gauss's law. And Ampere's law is used very much like Gauss's law. And since it doesn't have one, it doesn't have the other, I'm guessing. So what is Ampere's law? Ampere's law is a way to relate magnetic fields to current going through a wire. Now, because of some timing issues this morning, I don't have my demonstration for today. But, I think his name was Hans Christian Ørsted or something like that. Ørsted was doing a lecture, in front of a bunch of people. So he had his cool little experiment set up that he was going to talk about. Because, when a physicist gives a lecture, we like to have as many visual displays as possible. And so one of the things he had was a little compass up here. And we have learned that a compass responds to a magnetic field. And then he had a wire going from a power supply over to something else. And he flipped on the power, and he noticed that the compass moved when he flipped on the power. And so he's like, wait a minute. Compasses only respond to magnetism. I turned on the power, and it made the compass move. Maybe there is some magnetism involved to having, electric things. And so he did a bunch of studies and determined that when you have current going through a wire, it creates a magnetic field. So we talked about things like the electric motor. And we didn't talk about magnetic fields interacting with magnetic fields, primarily because in this class we never talk about magnetic fields interacting with magnetic fields. It just becomes too complicated for us. Instead, we said that there was a force between a current-carrying wire and the magnetic field. But now we see that we could have actually talked about it when we had that current going in a loop. It was creating a magnetic field. And when I have a magnet in the presence of an external magnetic field, there's a torque to make them align. And so Ørsted is the one who figured out that there is magnetism to moving charge. And then it's Ampère who came up with the equation to help us identify what is the magnetic field created by current going through a wire. Now, we talk about something different than flux in this case. With Gauss's law, we talked about the electric flux, which was how much magnetic field goes into or out of a surface. Ampere's law does not deal with magnetic flux. It instead deals with the thing that's called the circulation, which is the magnetic field parallel to a wire that goes in a closed loop. But before I move on, I want to mention Gauss's law, very technically, is Gauss's law for electricity, for electric charge. There's also a Gauss's law for magnetism. And now if you think about Gauss's law for electricity, I'll write down because it's not the strongest equation in most people's mind. Gauss said that the flux on a closed surface is equal to the charge enclosed divided by the permittivity of free space. There is a Gauss's law for magnetism, and the Gauss's law for magnetism, I'll write in a different color just so we can distinguish a little bit, says the magnetic flux, the magnetic field that goes into or out of a surface, a closed surface, is equal to, I believe it's mu naught times the charge enclosed. Now what is, current enclosed. Now what is mu naught? You don't know, right? You're looking at me like, am I supposed to know this? Is this something I'm thinking about? Mu naught has to do with magnetism, whereas epsilon naught had to do with electricity. So that is the magnetic permeability of free space. That basically tells you how much you can magnetize free space. Now something like iron has a much bigger mu permeability because you can really magnetize it a lot. But air, has our basic mu 0. Ion closed. Oh wait, not ion closed. I was thinking about my next equation. This is not ion closed. This is going to be I'll put B enclosed. It's really written a different way, but it gets you the idea. So B enclosed. What if we learned about how electric charge comes? It comes in what? It comes in monopoles or dipoles. You can have a single charge that's like an electron, minus 1.602 times 10 to the minus 19 coulombs, a proton plus 1.602 times 10 to the minus 19 coulombs, or you can have bigger charges. It comes, we call this quantized, by the way, because it only comes in certain values. So electric charge is quantized, but it can come as monopoles. You can have a positive charge or a negative charge, or it can come as a dipole having both. Magnetic charge, on the other way, how does magnetic charge come? Only as dipoles. Magnetic charge only comes as dipoles that are equal. So what's the net magnetic charge of a magnetic dipole? 0. Hence, what is the enclosed magnetic charge for any volume you choose? 0. Hence, this becomes a very simple law that just says for any closed surface, the magnetic flux is 0. Because for any closed surface, the magnetic charge enclosed has to be 0. So we won't even use Gauss's law for magnetism because it's very simple. It just says for any shape you choose, the magnetic flux has to be 0. So I'm going to now erase that because I don't even know what we should have put for that. I mean, we have a different way of writing it usually. So now back to Ampere's law. Ampere's law looks quite similar to Gauss's law. How did you calculate the electric flux in the non-calculus class? It was, okay, we have to start with summation, and it was electric field dotted to the area. It's important to have those arrows on top, right? If you don't have the arrows on top, it's not the correct equation. Because it has to be the electric field parallel to the area. And why do I have to have the summation? It's over a closed surface. And so I have to sum it over every piece of surface that closes it. So that's how we did the electric flux. Now for Ampere's law, the circulation is the sum of magnetic field dotted to, it's all looking really familiar, right? Except for it's not dotted to area. It's dotted to the length of each side for a loop. And that's equal to mu aught times the current enclosed. That's why I accidentally put mu aught times current enclosed above. And so that's what Ampere's law says. 14 days till spring break?
Yeah, school days.
See, she has written there for me, Ampere's law, 14 days till spring break. Just a little reminder to keep me up to date.
Yeah, I'll have it every day.
Okay. So this here is useful for helping us find the magnetic field. We are going to need to find a path that allows us to calculate the magnetic field parallel to the path, and then that will tell us about the current enclosed, or if we know the current enclosed, we can find the magnetic field. So let's go straight to a practical example of Ampere's law. Well, first we have the two equations that I just wrote. Now we'll go to the example. Oh, crud. This here is just comparing Gauss's law with Ampere's law to make sure that any familiarity you have with Gauss's law can be transferred to Ampere's law. So one has to do with electric field, one has to do with magnetic field. The electric field one applies to any closed surface. The magnetic field one is to a closed path. Two-dimensional surface for Gauss's law, a one-dimensional surface, a closed path for Ampere's law. And both of them relate the strength of the field, essentially, to how much is inside. One of us is how much charge for electric field, is how much current for magnetic field. And then, of course, you just have the mechanics of how you calculate it for the last things. So really, truly, this is going to have a wire. Yes. And Gauss's law. Now, this here is the calculus way, or not Gauss's law, Ampere's law. That's the calculus way of writing the circulation. Integral just means you're adding up each little piece. And the circle means a closed circle. So now imagine that we have a vertical wire. Magnetic fields, we learned, always have to do loops. They have to do closed loops come back on themselves. And so if we have a wire that's infinitely long, the only way you can make a closed loop that comes back on itself is if you make a circle to fit that symmetry. Any other shape, like a box, well, you rotate a little bit and it looks different. But if you have a wire, you have to have cylindrical symmetry. Rotating it can't change anything. So you have to have the magnetic field doing circles. There's no other option, just based on symmetry, right? It doesn't take any knowledge of physics, except for the magnetic field lines always close back on themselves. So they have to be doing circles. And so just like with Gauss's law, we had to carefully choose the shape of our surface we were going to calculate on. We have to carefully choose our loop we're going to calculate on. And since the magnetic field does circles, we'll make our loop a circle. Then anywhere on that loop, the magnetic field is equal parallel, either parallel or anti-parallel to the loop. Depends on which direction you're going. And the magnetic field can't change as a function of radius, because then you would break the symmetry, or excuse me, at a constant radius, the magnetic field has to be the same magnitude. Otherwise, you'd break the symmetry again. So we know that for a circle, the magnetic field here is going to be in a circle, and it's going to be constant strength. So I can do my circulation real quick. The sum of the magnetic field times the length for that circle is going to be equal to the strength of the magnetic field times the length of a circle. What do we call the length of a circle? Circumference, which is 2 pi r. And then that leaves us with no work, really, that the magnetic field created by a wire is mu aught times the current of the wire over 2 pi r. So Ampere's law instantly gives us the very simple result for the magnetic field created by current going through a wire. Now, of course, Ampere had to derive this law, and that's not so simple. And we didn't derive it here. What about the direction of the magnetic field? There are two possible directions. It could be going, if you look down on it, counterclockwise or clockwise. And so to determine direction, we once again use the right-hand rule. So right-hand rule, we had a right-hand rule for cross products. Now we're going to have our second right-hand rule, the right-hand rule, to determine the direction of magnetic field. And so to do this, it's really simple. You take your right hand, of course not your left, and you take the thumb of the right hand and point the direction current is going in a wire. So if, for instance, I have a wire that's going vertically here, I take my right hand and put my thumb vertical, and then I wrap my fingers in a loop around the wire. And, of course, I can move my hand around a circle. The direction my fingers are pointing at any location is the direction of the magnetic field. So that tells me if the current is going up, the magnetic field is going around in circles like this. And for any point, if I say what direction is the magnetic field here, I just rotate my hand so my fingers are at that point, and they're pointing this direction. If I want to know the magnetic field here, they're going that direction. So the right-hand rule, thumb is the direction of the current. You wrap your hand around the wire, and your fingers are pointing the direction the magnetic field is wrapping around the wire. Clear enough? Because we totally have a clear question on the next slide. I think it's on the next slide. It might be 3 slides from now for the way my memory goes. We'll see. It's totally on the next slide. A wire is carrying current to the right on the screen. So you have current going like this. And it's asking you for what the magnetic field is at this location here, what its direction is. So I will even label by answers. That's A, that's B, that's C, that's D, that's E, and that's F. And of course, G is none of the above. What was that? E is a circle with a X in it. Yeah, it's supposed to be the fletchings of an arrow going away from you. So it means going away. Okay. We still have a handful of people. Okay. All right, so we had 5 people said answer B for down. 1 person said answer D for to the left. 11 people said into the screen. Now let's look at these to try to evaluate how people got the answers. We'll start with the answer that had the fewest. To the left. How do you suppose the person got that? I'm obviously not asking the person who said to the left how you got it. I suppose they got that. Yeah, they must have just said opposite direction of current. But that is not the way it works. The magnetic field is not parallel or anti-parallel to current. So it wouldn't be either to the left or to the right. It's perpendicular to the current. So then we have B, down. It is perpendicular, but it's still not correct because we have to use the right-hand rule. And underneath, if your fingers are pointing like this, underneath, we're pointing into the stream. Question, Helene?
So if it was above, it would be like out of the stream?
That is correct.
Okay. Okay.
You have a question, Austin?
No, I was just trying to twist my arm.
Yeah. Once again on the test, rotate paper rather than going like this. Okay, next slide, not question. The correct answer was that it was going into the screen. All right. A single coil is a little tricky. We can't calculate the magnetic field due to a single coil using Gauss's law without being pretty good, because we don't have a nice exploitable symmetry there. It's a circle. Circles, there's a symmetry with a circle, right? But I need to find a path that's going to go through the center of that circle that has a nice symmetry for me and forms a loop. Excuse me, I'm so sorry. Keep hiccup. We can't really find that. So I just throw to you what the answer is for the magnetic field at the center of the loop. Now notice, if I have that wire, I can take my fingers and go around the loop, and on the inside of the loop, my fingers will point in the same direction every location, every time. Right? So I go around, my fingers inside will always point in the same direction. So the magnetic fields inside add up together to make a stronger magnetic field when you have a loop. On the outside, the magnetic field on the outside, and I will just draw here, the magnetic field on the inside was going up here. On the outside, it was going down. So if I have a circle, the magnetic field on the inside coming up, outside going down. We can see that on the inside, they're all going up and they're all adding together. It's going to get stronger. On the outside, it's not so obvious. If I take this top one, the magnetic field on the outside due to the top one is like that. Right? Because it's, if your fingers are going, oh, I do need to have a direction I implied in my head, but I didn't write it down. If the current's going like that on the top, my fingers are going, my thumb's like this, the fingers wrap around, and my fingers are pointing out below, and this is below. And so I have the magnetic field from the nearer part and from the farther part are in opposite directions, which is going to make a weaker magnetic field. So the magnetic field outside of a loop is smaller, but the magnetic field inside always is bigger. So when we talk about the magnetic field for a loop, we tend to start to forget that there is an outside portion. And we just talk about the magnetic field inside. So if at some point you read a question that says, was the magnetic field created by this loop? They meant on the inside, because they just forgot that there was an outside. So for the single loop, the magnetic field is mu naught Ni over 2R. Now what is N? Well, if you have more than one loop, it's going to be bigger because you have more than one loop. There is a difference between that and a solenoid. A solenoid is a coil that has a length to it. Right? The loop had no width, if you will. It's saying all these loops are right on top of each other. They're not spread out. It's not taking up space. A solenoid is more realistic if you have more than one coil. Right? Because how can you have two coils and not take up space? So the solenoid is more realistic. It has some shifting to the side. You still have each wire is going to make a magnetic field that adds up to be very strong in the middle, but is weak on the outside. For a solenoid, or I'm going to go back a picture, for the single loop, we use a third right-hand rule to determine the relationship between current and magnetic field. Why a third one? Just to make life a little shorter and more complicated, probably too. So we've already learned I can take my hand, put my thumb in the direction of what? For magnetism, I put it in the direction of current. And then my fingers wrapped around the wire tell me the direction of magnetic field. Well, a new variation on that is take the same right hand, wrap your fingers in the direction of the current in the loop, not in the wire, but in a loop, and your thumb points the direction of the magnetic field in the center of that loop. It comes from the first one. If you don't want to learn the second one, you don't have to because it comes from the first one. But it's just a quick way of saying, okay, I have a solenoid or I have a loop. I just wrap my fingers the direction the current's going. So in this picture here, the current is coming down the side toward us, which means going up the side away from us. So I wrap my finger so it's coming down the side toward you. And my thumb points this direction, saying that's the direction of the magnetic field.
How come on this one you don't have pi anymore?
Like I said, it's not the simple geometry like you did for a straight wire. And it comes from the fact we have to do it a different way. I should say, the reason we have to do it a different way is because it's a different situation in the pi is, it's not the way we do our math, but we have to do our math different because it's a different situation. Okay, so how do we find the magnetic field created by a solenoid? Well, apparently we do it next class period. Solenoids are very common in life. We have them in our cars as part of our ignition system. If you go and have an MRI, which I have had done, they need to make strong magnetic fields, and they use solenoids for that. So they are very common. Also, inductors in electric circuits are solenoids. So they are one of the many common things we learn about in physics, and so we'll learn how to analyze them next class period. Back to this one or one before it? Well, I have lab from 2:30 to 5:30, and I have a TA, so I'll probably be available for help during that time.
Not on purpose. Did you get that Facebook thing I sent you? Oh, I found it.
Yeah, I know.
Yeah, here's where the key is.
Okay.
Exam 152, 2016, exam 1 key.
Okay. I just needed help with 5 and 6.
Homework? 5 and 6? There's a sixth problem? Oh, yeah, there is, because it was a long weekend and I didn't give you one the time before. Yes, let's go to my office.
All right.
Yes, sir.
I was here like a minute late.
Okay, so I marked you down that way. I know you were here in the end, and so that's why I was asking you. I know I'm going to be wrong if I stick with what I
I was
have.
here waiting for them to finish the test, and then I went to talk to McNeil about a project we're having.
All right. What time will you be coming by?
Let's get together. Yeah, we're just going to do that.
Okay, I get it's my time.
Sure.
Yes, Bridget,
still meeting.
you didn't do number 7.
I know. I yeah. Are we still meeting?
If you want to,
Yes.
absolutely.
Yes.
I forgot to stop my recording. That's still on the recording.